11.2 Relative motion in two dimensions. In Physics 20, we will look at two kinds of two-dimensional relative velocity problems. We're going to look at boat problems and plane problems. In both of these situations, we have an object moving within a moving medium. For example, a boat moving in a river. If the boat is trying to cross the river, the boat has its own speed. We'll call this the boat's speed. But we have to remember that the river also has a current, and the boat is moving in it. This is the river's velocity. As a result of the combination of its speed across the river and its velocity, the boat experiences an actual route that's at an angle to where it was trying to point. In plane problems, we have much the same situation. You have a plane applying its speed in a particular direction. However, we have to take into account the wind speed as well. As a result, the plane ends up at an angle to where it actually was pointing. Its actual velocity is at an angle to its direction of motion. This is best understood through examples. Our first example will be a boat problem. Your boat has a still water speed of 8 meters per second. Now, in these boat problems, we're going to assume that the boat only has two options, on and off. And when it's on, it can only travel at 8 meters per second. It's a really weird boat. You point your boat directly east across a river and try to apply that 8 meters per second in that eastward direction. The river is flowing at 5 meters per second to the south. It's best to draw a picture of the situation to try to understand what's going on. We have a river that is flowing south, and you're trying to point your boat directly east, applying its speed of 8 meters per second in this eastward direction. But because the current is flowing at 5 meters per second, as a result, the boat ends up moving at an angle to where you pointed it. This is a relative velocity problem because we have 2 points of view. We have the point of view of the water and the point of view of the shore. And we have to consider the different velocities from the different points of view. The velocity of the boat relative to the water is this 8 meters per second that we're applying. The velocity of the water relative to the shore is 5 meters per second. East and south. The velocity of the boat relative to the shore is its actual velocity that we're looking for. We'll redraw this triangle so you can see how the calculation is done. It's a right angle triangle. And we're looking for the hypotenuse. This is the velocity of the boat relative to the shore. This can be calculated using Pythagoras' theorem, where 8 squared plus 5 squared square rooted gives us the velocity of 9.4 meters per second. The angle is calculated using tan. Tan -1 of 5 south divided by 8 east gives us 32 degrees south of east. So the velocity of the boat relative to the shore, which is just another way of saying the velocity that an observer on the shore would see, is the 9.4 meters per second at 32 degrees south of east. Part B of this problem asks, if the river is 25 meters wide, how long does it take the boat to cross? The velocity triangle we established in the first part of the problem was 8 meters per second to the east, with 5 meters per second to the south, resulting in 9.4 meters per second at an angle of 32 degrees. This is the velocity vector triangle. For every velocity vector triangle that we have, made up of its 3 components, there is a corresponding displacement vector triangle with matching angles and sides. We don't know all the sides of the displacement triangle, but we do know directly across the river is 25 meters. And we do know that it has a matching angle to our velocity triangle of 32 degrees. You can use the formula v equals d over t, because we're talking about constant velocity here, on matching sides of the 2 triangles. So for example, the 2 horizontal sides are matching sides. The 8 meters per second matches the 25 meters. For this reason, we can use v equals d over t to find t. T is d over v. It's 25 meters divided by 8 meters per second, which gives us 3.1 seconds. In part C, we're going to ask, how far downstream do you end up? And again, we look at our matching triangles. The velocity triangle is 8 meters per second to the east, with 5 meters per second to the south, combining to make 9.4 meters per second at 32 degrees. The corresponding displacement triangle is 25 meters across at an angle of 32 degrees. And we're looking for how far down you end up, or the distance in the y direction. Now, these are our 2 matching sides, the 5 meters per second and the dy. But to solve this, we need a third piece, we need time. It's important to realize that time is not a vector. Time doesn't care about direction or which way you're going. As a result, the same time can be applied to all sides of the triangles. So the 8 meters per second takes 3.1 seconds, the 5 meters per second takes 3.1 seconds, and 9.4 meters per second takes 3.1 seconds. So if you find the time on one side, you can use it to all the other sides. Since v equals d over t, d equals v times t. And this is 5 meters per second times 3.125, which is the unrounded version of our time, which gives us 16 meters. So the distance downstream you end up is 16 meters. These boat or plane problems come in two forms. The last form we looked at is the easier form, but there is another way we can look at it. I call these two problems the smart navigator and the dumb navigator. What it really just means is the dumb navigator is like in our previous example. They don't realize the current is going to push them down. So they have a river with a current, and they still try to point their boat directly across the river. And even though they're pointing directly across the river, because of the current, they end up at an angle from where they intended to go. So from the point of view of the shore, the boat ends up downstream from where it intended to be. The smart navigator knows that there's a current, and as a result, points their boat to try to defeat the current. So they see the current and they decide, if I want to end up across, I'm going to point my boat at an angle to that current to try to beat it. So they point their boat at an angle. And as a result, their actual motion ends up traveling straight across. And the boat ends up directly across the river. The smart navigator points at an angle to get across. The dumb navigator doesn't think to point at an angle and instead points across and ends up downstream. Here's another example, and for this example we'll look at a plane problem. We have a plane that can fly at 100 meters per second in still air. The plane encounters a wind that is traveling 40 meters per second to the north. At what angle should the pilot point so that the plane ends up directly west? Now this pilot is a smart pilot. The pilot knows that the plane has to be pointed at a southwest angle so that the plane counteracts the northward wind or defeat the north wind and end up to the west. So in examining the northward wind, of 40 meters per second, the pilot points their plane at a southwest angle with their 100 meters per second. As a result, the plane ends up traveling directly to the west. we say the velocity of the plane relative to the air is 100 meters per second. This is the velocity of the plane from the point of view of the air, and we want to know its angle. The velocity of the wind relative to the ground is 40 meters per second. This is the velocity of the wind from the point of view of somebody standing still on the ground. Here's the vector triangle for this problem. 100 meters per second is at an angle. 40 meters per second is one of the sides, and we're looking for this angle. The 100 meters per second represents the hypotenuse of this triangle, and the 40 meters per second represents the adjacent side. Cosine of theta equals adjacent over hypotenuse. So cosine theta equals 40 divided by 100. Theta is cos negative 1, 40 over 100, which is 66 degrees. Now we need to decide whether this is south of west or west of south. So if we draw in our vertical line, which is what our angle's between, and we see that we're west of the south line. So we would say we're west of south. So the angle the pilot should point is 66 degrees west of south.